lattice gauge theory community, first of all, was so poor. Does this work? Yeah. Was so poor that we had to build our own computers because nobody would buy them for us. Actually, the first computers that I did in lattice gauge theory were borrowed. Sometime we would find unused computers that the computer company hadn't sold them yet, but they were still running. And we'd go in and use their computers to get some free cycles. So gradually got into computing, and then finally ambitious enough to have funded a special purpose machine in Brookhaven. And at this point, the Department of Energy says, even though this is a hard thing to program, everybody in the United States must be able to use it. And so they said, well, we will actually get you into the SIDAC program and try to make a more generic community code. Where have we heard this before? So that anybody who's in the community can run efficiently on this new architecture. So in some sense, we've been at the crisis point of working on new architectures from the beginning because we were building the new architectures. And I can tell you, if you think a new architecture coming from a company is unfriendly, believe me, when it's built by a bunch of theoretical physicists, it's really unfriendly. So that's how, in the process of this, somebody said, well, we got to coordinate these folks that have been adamantly, independently writing all their own code. Why don't you do it, Richard? And that's how I got into this. So you see that here's the topic. This is a picture from the, I have to keep track of my time here. This is a picture from the LHC, the big experiment in Geneva. And that's the aftermath of two little protons coming together and hitting each other and creating matter, because energy is mass when you set C to 1, according to Einstein. And so if you have enough energy, you make things. And so that's just an indication that there must be something fairly complicated in the dynamics of two protons if you put them together and suddenly they start spewing out all kinds of stuff. That theory of the proton is quantum chromodynamics. And that is the theory which is beyond anybody's analytic capabilities to make predictions, even though a lot of particle physics is done by Feynman diagrams and a lot of analytic work. So here's the outline of my talk. I'm going to talk a little bit about the physics. I'm going to make you all into particle physicists in the first 10 minutes. And then I'm going to talk about architectures, because we are hungry to get as many cycles as possible, and therefore we optimize our code ruthlessly. But of course, as the architectures change, that makes it hard. And as I explained, we've gotten a little better at that, but I think we need to learn a lot more. I hope that the computer scientists will teach us better practices. Even though we think we know how to do it, we can always take some guidance. I can see people do it better than we do. So, and then finally, I'll get to the software part, which is, after all, the glue that keeps the physics and the hardware talking to each other, and in a sense is absolutely essential, the whole thing. So I view this activity, as you can imagine, is very interdisciplinary. The difficulty of this interdisciplinary activity is twofold. One is, most of us are trained in one discipline and can barely understand the language that another discipline talks. But the other is that each discipline is a vast territory, and when you want to collaborate, you have to find some common space in the middle, a tiny space, right? Highly unlikely to find two people that actually not only can understand each other, but sit in that space. And although they may be very smart and very useful in their own field, if they don't sit in that space beside the entertainment of learning another subject, you can't do anything. And I think actually the funding agencies don't understand how complicated this mating process is. You really probably, I talked to mathematicians and computer scientists, and it may take 3 or 4 years before we really find that intersection. And then suddenly something really great happens. So I'm not saying it's not worthwhile. I'm just saying you have to be really clear that you're talking about the same thing. But nonetheless, that's a very exciting space, and I think many of the people here would like to be there. And we, of course, we all complain that it takes great expertise to sit in the middle, and we should be good jobs for such people. But of course, universities love to put people in one of those big circles. and if you're very good in the middle, they almost blame you for being good at the other thing. I mean, it's, no good deed goes unpunished approach, right? So, okay, so I'll start quickly with physics and try to give you at least a sense of where the physics is. So let's start with the real world. So we've been hearing about these electrons whirring around. They obey Dirac equation, and they're complicated. The one thing, however, is that the charge on the electron is in some sense weak, and we've just been hearing that you can do a lot of wonderful approximations because of the weak charge of the electron. It doesn't mean it's simple, because if you've got many electrons going around, let alone many nuclei making molecules and so on, it gets a many-body system. I'm not trying to make it simple, but you do have a starting point where you can really kind of visualize what's going on. You really do have these electrons orbiting around, obeying the Schrödinger equation, more or less. Now, inside here is a bunch of nuclei, protons and neutrons, and then there's the whole area of nuclear physics, but that's really starting to be the area of the strong interactions, or QCD. But really strong interactions occur inside a single proton, because actually the active players are themselves Dirac particles called quarks. Now this quark and this electron, if it were free, just running through space, obeys essentially identical equation, except for usually we use the Dirac version, which is the relativistic version of the Schrödinger equation. So the last talk we had the same equation as here. The difference is this is interacting with a soup of very strong forces. And the reason that we want to understand these things are two. If you really want to understand the nucleus, you should first realize that the proton is this complicated orbiting object of three quarks plus a lot of so-called gluons holding it together. And then you need to put them together into clusters, and there's a whole area of applying this to nuclear physics. But on the other hand, in that earlier photograph where we were just colliding one of these objects, it's also necessary to understand that, because all the clean theoretical predictions are predictions for a given quark hitting another quark. But of course, you can unfortunately not make a beam of quarks. It's a very weird situation. The elementary particle physics has gotten to the particle of nature never can be isolated. It's elementary, but it's always inside. So you can never do a clean experiment with it, right? There's only dirty experiments. You take a big proton together and try to figure out after it's whirring around inside this mess what it really meant to do when it just hit dead on something else. Or you can't discover new physics. So high energy physicists keep trying to figure out the effects to get rid of the effects of all this complicated internal motion and unfold it, right? And so on. So if you're a nuclear physicist or high energy physicist, you want to do this. Now, the theory for this is amazing. It's like the Maxwell equations. Here's a T-shirt. We like to not write our Maxwell's equations as 4 separate equations, but one, by letting the indices run from 1 to 4, space and time. So there's really only one Maxwell equation. It makes it simpler if you count to 4 instead of to 3. But the only difference between the Maxwell equation that we heard about in the last talk is our Maxwell equation is not linearly related. It's not just a sum of terms in the field. The normal Maxwell equation just says that something like the magnetic field is the curl of A, and this is just a more complicated thing where the curl is a 4-dimensional curl in a Maxwell equation. But there's another term, A squared, in our Maxwell equations. It's so-called non-abelian. So that means that there is no electromagnetic waves going on because it's charged among itself. So if you try to propagate this Maxwell field, it produces more photon-like things, which are called gluons, which then interact and make this strong force and bind the nucleus together. So there is no linear regime for this Maxwell equations. But mathematically, it's very similar. So what happens is an amazing thing. In the case of the standard Maxwell equation, the approximation of Coulomb's law says that when you take two charges apart, it gets weaker, just like 1 over r. A Nobel Prize was given because this Maxwell equation does the opposite. As you pull them apart, the force gets stronger. Because when you pull it apart, it makes a plasma which binds them together. So it's just the opposite, okay? This force is weak when you get close and strong when you get far. And that, of course, makes the whole problem different. I mean, turns it on its head, right? So you can't, and that means you can't get the quarks out. Now, Just as a sort of, I keep telling this because somehow in my community, people don't often respect computing as much as they respect people who write down analytic diagrams. All solutions to field theories are algorithms. On the left-hand side is Feynman doing Feynman diagrams. And then he worked for Connection Machine because he realized that eventually you have to start to do some calculations. On the right-hand side is Ken Wilson, who invented the field, and he spent most of his time developing very fantastic variations on the Feynman diagrams. So there's actually no disconnection at all between the analytic methods and the numerical methods. Anybody's career that's decent zigs back and forth between those two sides. I don't know why we call them different. Okay. All right, so anyway, here's the crowd of heroes in this field. Now, this field was invented in terms of a numerical method in 1974. So we've had, what, 40 years of trying to figure out how to write better codes. I must say that during those 40 years, we didn't get many results because the problem was so hard that the fastest computers, even with the best methods, were still too weak. And indeed, Wilson warned us that this was going to happen. Even several years after he invented it, in 1989, he said, we need 10 to the 8th increase in computer power. And actually, he abandoned the field and went into chemistry, which his father was in. Actually, his father was a chemist at Harvard. And because he said, I'm not going to deal with something that I have to wait that long for, okay? But there's other part of his sentence which is never often read by people enough, and spectacular algorithmic advances, okay? He meant we want the product of both. We want to get a 10 to the 8th by being smarter in the way we do it, times the 10 to the 8th. Now, the amazing thing is he timed this to be 25 years development in chemistry, and we're actually already there. So the hardware people have beat us to the algorithmic punch. They've actually given us what we need. Now we have to see if we're smart enough to use it, okay? Okay, so just a little more on how you have equations. We have differential equations like anybody. The one difference, maybe I should go next slide. The one difference is that there is no boundary in this. We're doing space-time. And space-time is infinite this way, this way, this way, and forward and backwards, okay? So we don't have a problem of strange boundaries. We have differential equations in a flat, infinite space-time. Of course, we can't make it infinite, so we wrap it around periodically. And in fact, we consider it infinite if we have like 32 or maybe 100 sites in one direction. Remember, we have to multiply in 4 ways, right? So we have 4-dimensional crystals. If we choose, we can make this lattice exactly symmetric because there is no natural place in which it's different from any other place. And indeed, it's an advantage because the real world doesn't know where it is, so at least this crystal has a discrete translation. So we keep a symmetry approximately that if we move from one place to the other, I do experiment here and I do it in the next room, I should get the same answer, right? So that's part of the symmetries of the problem, and it's better to have a discrete version of that than none at all, right? Now, of course, once you put differential equations onto a grid, you do finite differences. Here's just the standard derivative. For some reason or other, mathematicians call the spacing h, and we call it a, but that shouldn't be a huge barrier. Now, the next thing we have to do, though, is we have this Maxwell field. And the Maxwell field is this potential A. It's sometimes called the vector potential. And however, it turns out, because of gauge invariance, it's linear. It's a linear if this were an infinitesimal interval, but it actually has to be exponentiated to give the right properties when you make a finite jump. So you have this phase factor. So what happens is that we end up having differential equations with phase factors. Now, there is a nice feature of this. These A's are actually elements of the SU3 Lie algebra. When you exponentiate them, they're SU3 matrices. So these are nice, compact rotation matrices. Well, actually, not quite rotation, because rotations are SU2, not SU3, okay? So you have fields time rotation matrices. And notice that they really live not either on X or the next site over. They really have to be associated with a link. So the result, and this is Wilson's result, is that fields, normal fields like densities or the Dirac equation, lives at sites. But then these gauge fields, the Maxwell's fields, live on the links. So it's a slightly more complicated set of differential equations. We have some variables on links and some variables on sites. But really quite simple. I mean, in a first week, you can teach somebody how to put this on a lattice. Then they can spend the rest of their life trying to solve it. Yes?
And when you say links and sites, I might say edges and vertices.
Exactly. It's a graph, yes. Yes, actually, I teach algorithms even in computer science-like courses, so yeah, I can use that language too. It's difficult being bilingual, right? Yes?
For consistency, if you go back to your equation,
yes, right.
Is that exponential applied to the gradient, or it's actually to only the advance, so the next?
Technically, what it's doing is the following. This field, well, okay. What's your background? If I can use the right language, what's your background? You know what gauge invariance is? Is that a familiar idea? Well.
No, but what I'm saying should be parentheses over there?
No, it shouldn't be. What you're actually trying to do is make this piece and this piece transform the same way. Okay. But it really is. Non-abelian gauge theories actually have more or less the conceptual structure of general relativity. They need transports, and they have curvature. And so the right language is to think of it in a differential geometry thing. So actually what the Maxwell field does is give a gauge curvature to the space. And this is the transport, okay? And in fact, you can write F as a commutator of transport. So if you have any differential geometry in your background, then that's really the way to say it, but okay. So that's what it's doing. So, and by the way, you see, if I expand it out linearly, then I get this. And this was the thing I just crudely wrote over there. This is the normal part you would have for Maxwell if it were electrodynamics. And this is the nonlinear part, which is actually a commutator. I cheated by targeting a square, okay? So this is the full nonlinearity. And you see what's happening is the algebra of these phase factors in the group are giving you an approximation to the commutator algebra for the Lie algebra. So it's very important to keep as many symmetries represented as a discrete example of your continuum you want to get to. By the way, that was the reason that I had this little byline in the top, is that the art of exact approximations. Okay, we approximate it when we put in the lattice, but we look scrupulously for anything we can keep that is partial and exact. And in quantum physics is very important, but that's another lecture. Okay. Anyway, let's just get the feeling of how you put it on a lattice. So you get on the lattice, and first of all, you can see that from the point of view of parallelization, finally you have exactly the same equations distributed on this lattice. And the lattice could be 100 on each side, and that's 10 to the 8th. So you have 10 to the 8th things to do simultaneously, because we're doing a probabilistic update of these fields by Markov process, exactly the one that was described last time, except for now it's completely uniform. So if you ask, can we make this parallel? Yes. It's just obvious. You look at this thing, we've got 10 to the 8th things to do in every cycle. It's actually more because there's a lot of algebra at each site as well. So in fact, for a long time when we put these on clusters, we couldn't afford to do that because there's not enough work on a single node, right? But the GPU actually has such lightweight threads that we literally parallelize on each point. So we can fill any number of cores in the sort of GPU land with just great ease. So the result, for example, is we put this on the blue gene L. We could see the Q as well. Scaling is just weak scaling is just linear, okay? And indeed, as soon as we know how to run it on 4 nodes, we can predict what it's going to be like on 10,000 nodes. It doesn't change. It's homogeneous. Okay. If the machine is homogeneous, then we love it. Okay. Now, by the way, you see what's happening. The point of my talk will be actually to point out that our algorithms and our machines are becoming inhomogeneous. Okay. So our ideal paradise that we've been living in is about to collapse around us, and that's part of the new algorithms and the 10 to the 8 that we need. So simultaneously, we're in a perfect storm. Our algorithms need to be more subtle and take into account domains, and the machines have become more subtle. So we've been, and so the part this, we've always been accused, oh, your problem's too simple. Well, unfortunately, that's a past statement. And so I want to show you why that's a challenge and how we're meeting it. Okay, this is a real simulation. This is the force between two quarks. And the linearity of it is that as you pull them apart, you're building up this huge field of energy in between them. And so that's a graphic of the field strength. Instead of being like Coulomb law, which would die off very weakly at infinity, it's actually, in fact, it's the reason that strings were first invented for this, because it looks for everything like a vortex string. Okay. Now, that is only part of what's happening. The gluon itself in the background is interacting. And these are snapshots of the probability distribution in a three-dimensional slice of my four-dimensional world. So this is the intensity of the electric and magnetic fields, basically, okay, as we go through the quantum process. So you see that even though our lattice is very uniform, we're trying to solve equations in a very noisy background. And we have to resolve them every time we sample the background, okay? So that's why the problem is hard, okay? If it were just weak charge, we'd have nice regular grid. We'd just use any old library package and we'd solve this with a great. The first machine that was really designed, I think, in a way for QCD was the connection machine. Actually, Feynman went and worked to him. By the way, this T-shirt here, the reason I've got this, you can get the T-shirt. You can't buy the machine anymore, but the T-shirt still lives. They've reissued it. Okay. Now, what happened, of course, was that the vector machines got killed, not by thinking machine, but really by Intel processors, right? And so suddenly, the nice vector programming, which was closer to parallel programming than we've had since, got killed because the microprocessor was cheap. We descended to assembly language, which is called MPI, and we've been sitting there all the time. And we, of course, followed the trend. And this, as I said, we built our own Beowulf cluster, more tightly coupled, called the BG, the QCD-OC, with collaboration with IBM. Then they said, let's do it right, and made the BGL, the BGP, and the BGQ. But it's really the same architecture. It's not accidental that we find it very friendly, because we actually designed the architecture. Okay. Now, it's useful for other things, and they made it a little more general. By the way, this thing was much more flaky than this, so it's nice to have engineers. Okay, so anyway, this is fine, and we lived in this paradise, and now, as I say, things are changing. It's changed on the architectural level, but it's changed. Now, part of the change, by the way, so there's big machines. I'll go fast. Okay, now, we have to do software. So here's programmers. You've got to connect the theory to the machine. Of course, this is when the program was not stored, but was actually just in the people plugging in. Pretty von Neumann, I guess. And so we have to get together programmers. And as I said, we needed a whole community to do this, although we were all writing them sort of independently. So here's just a snapshot. It's not the whole community, but here's a snapshot of the sort of crazy people who work together on a community code. And maybe you can tell by their nonchalant style that they're not exactly easy to get going in the same direction. They, people say I'm herding cats. That's probably optimistic. But that's sort of the side. Actually, this is not the whole group, but I mean, I would say that the number of people that are sort of actively developers are probably 40 or 50. The really good hotshots are probably a dozen, and then the users are larger numbers. It depends what I mean by hotshots, people who can write at the low level and get the last inch out of the machine, okay? Of course, many people develop algorithms and applications. Now, in the process of doing this, and making it available to everybody, we had several different application codes. There was CPS, the Colombian code. There was MILC, which is a whole collaboration. MILC it means MIMD. It was actually a cluster code. And then another one, which was actually called ZIN, which is Hungarian for color, got translated, believe it or not, from, I believe, some kind of Fortran into basic C, and then this became a highly templated C++ code. So this is highly templated C++ code. This is C++, but really only a rather thin veneer. It's sort of what some people would call physicist C++. This is entirely C code, and we have a division of disagreement on whether one should use C++. But we had these codes, so we had to build layers underneath that would move ourselves more quickly from one architecture to the other. So in the bottom, we made a subset of message passing because, in fact, our original machine did not have MPI on it. And we also had gigabit Ethernet clusters. So we had to write our own things. And we also wrote faster things for the BGL because part of our group was actually developing the network. So they knew how to do better than the MPI, at least in original. So this is our message passing layer. This was linear algebra. We have a lot of compact linear algebra. It's basically vectorizing linear algebra routines. Then on top of it, we make a data parallel language, if you like, for our thing, so that we look at the whole grid globally, and it's automatically split up into whatever subunits we are running on a particular machine. And we can usually configure that so that each subunit is exactly equal, so load balance is no problem. We have threaded libraries, which came in later, but since now we have large nodes which need threads, we have threaded libraries. We wrote our own parallel I/O because we couldn't find good enough stuff. But all of this does cost something in terms of ruthless efficiency when you go from one architecture to the other. I mean, it's a generic message passing, vectorized language, if you like. So we always have the very important inversions of the Dirac matrix, this propagation of the quark through the media. And so we write these things often in assembly language. So for example, in the BGQ, Peter Boyle works directly with IBM, actually in the design of the BGQ, is running on the simulator before it even existed, and wrote extremely finely tuned linear algebra routine for the Dirac operator on the BGQ, which means one of our application codes gets probably 2 to 3 times the performance of the others on at least the majority of the code, not entirely across the whole thing. These are domain wall fermions. This is Mobius fermions. Now here is now another package. I'm not sure where it should be put, actually. This layer is not completely. This is our code in CUDA, C-U-D-A, which unfortunately we call ourselves CUDA, which leads to complete confusion, Q being for quantum chromodynamics. I know what UDA means. But this is a whole library which basically gives us all of the special routines that we need if we want to run on GPUs. It's a multi-GPU library. And then there's all these applications codes. And, okay. I guess I'm saying all of this. So, I mean, to some extent, we can do algorithmic development. We can do algorithmic development in terms of linear algebra and so on at this level pretty much in terms of new ideas. And then if something is extremely important, we'll plug it in with assembly language code. Okay, so, we drill through our interface, if you like, when we have to, okay? And those particular codes will just be specific to an architecture. Okay, so that has been very helpful, and it certainly means that we've been able to move from one platform to the other rather rapidly. It's clear, CUDA is an example, that with specialized architecture, we had to have a whole subgroup working on this thing, and it wasn't just a simple, port of our basic architecture. Although amazingly, there's a just-in-time extension which has taken the entire Chroma package and without the fierce efficiency of this code has ported the entire code to GPU. So we do get in some time and use source-to-source methods to port the whole library. Okay, so this is our strategy. Now, I want to, in the remaining time, which I just have enough, I want to talk about 2 things a little more detail. One is the realization that treating our grid as a uniform grid for our inverter, which we actually usually use Krylov conjugate gradient inverter methods, is actually not the fastest way to invert a matrix or to solve linear algebra equations. And in fact, the fastest way we've known for actually about 20 years should use decomposition a la multigrid, okay? And in fact, we tried to do this for about 20 years, and we couldn't figure it out. So this is a really a great story in the sense that I was involved in the 20 years ago and not doing it right, not quite getting it to work. And this is a case where David Keyes came finally to me and said, I got some smart applied mathematicians who have been thinking about multigrid more than when you were last learning about it, which isn't surprising. And we realized that they invented something which was slightly more powerful than what we were trying to do. As usual thing, you know, in an algorithm, one loose screw and you lose, right? So they realized that we needed an adaptive method because we really have a matrix with non-uniform coefficients. Actually terrible, complex matrix coefficients, not even just, you know. So multigrid is more complicated if you don't have a uniform problem. And you can't really, well, people have tried to design sort of a priori ways to break up a linear operator. But after a while, it gets beyond you. And what you have to do is you have to have an adaptive method. You have a method which, when you run it, it finds the approximate multigrid operator. So here's the style. So here's sort of before and after. If you have a very simple differential equations, now it's in one dimension. It's a very clear idea in multigrid is that, you know, you would like to solve this thing on as fine a grid as you can afford, as many, many points as you can. But you know that if the coefficients in this equation are constants, which they are, this is just the Laplace operator in one dimension, then, and if you have some, you know, simple boundary conditions, then the solution is going to be some smooth curve. After all, that's the reason you have a fine grid, is you think that the fine grid is interpolating more and more accurately against a smooth solution. So it should be possible to approximate this finer grid here by a coarser grid if you could isolate the part that was smooth. But then you have luck. When you start in an iterative solver, the first thing it does is look at the neighbors and smooth it. So in fact, when you start with a solution of an iterative solver, every single local iterative solver, doesn't matter what it is, the first thing it does, it gets rid of the high frequency modes, okay? And so very soon, it is now in a subspace of smooth functions. So then you say, oh, now I will write the operator in that subspace of smooth functions, and I will double the lattice spacing. And this is called a grid transfer from H to 2H. I've used the math terms, okay? So you just have to find this operator. Now, in a simple case, it's pretty clear. You had here the lattice spacing H, you change H to 2H, do a little fiddling, and you know the new operator. But what if these coefficients in front of here are wildly fluctuating? The thing is still trying to, quote, smooth, but what it's really doing is it's getting rid of high eigenvalue components and making it rich and low eigenvalue components. But you don't want to be able to, you can't solve the eigenvalue problem first. To find the eigenvectors, that's would be worse than even inverting the whole matrix, right? So what you have to do is you run the algorithm and you get against zero, and you isolate a candidate near null vector, a candidate low eigenvalue. Then you use that as a mask to project down to the coarse level. And then you try it. And if you have a multi-component equation, which we have 4 spin components, 3 color, and so on, you'll find that masking and coming down to a single equation won't work. So then you try again with your new algorithm using the lower one, and you look for another smooth component. But fortunately, this only requires getting a few. We find about 20, okay? And then at that point, you've not taken a single value down here, but you've made a 20 by 20 block dense operator down here. So it's block dense, but it's still sparse along the big lattice. And so that is called adaptive multigrid, okay? And it turns out it was just what the doctor ordered for lattice gauge theory. But clearly the idea, actually, this was done with a large group of applied mathematicians. I'll show you the whole list. Okay. here's our gang. We sometime even met together in a single room, okay? But so they're very aware that this is a sort of generic thing. But I was actually told, at least by Rob Falgood, who is the hyper leader. That,
He was here last week.
he was here last week, okay. I was told by him, well, like I can ask him again whether he still says this. I said, well, this is a great idea. You must be applying this all over the place. He said, no, you're the first application that's used it. He was very delighted, okay. But I think that's actually probably because other people have been smart and worked around it. I personally think this is a good example where we should throw this idea back to other fields. Because rather than sweat over trying to find special boundary conditions and ways to keep jumps under, we have a very noisy background. My guess, but it's never been tried, is that this method is actually a very general kind of a black box approach to constructing multi-grid operators where they're hard to construct. This is certainly a hard place. And by the way, so anyway, what happens here, by the way, in our earlier experiments with this, with 20/20 hindsight, we can see exactly what was going wrong. We actually followed this Wilsonian idea, which I mentioned when he went over to field theory. Blocking a lattice down is called the renormalization group in stat mech and in particle physics. We have always had this idea of going from fine to coarse, or we, I should say, since Wilson and Kadanoff and these breakthroughs. So we always built a hierarchy of theories, and indeed it is precisely the reason that we know the shape of that curve I showed you that is confining curve. We know exactly how that works in a weak coupling renormalization group. In fact, it's one of the analytic exact answers which we always make sure we agree with to make sure our codes are not stupid, okay? So we thought, okay, fine, we understand the idea. What more do we have to learn from applied mathematicians? And we started down this road of renormalization group. But somehow we forgot the next thing that Wilson told us, and that is that it's not weak when you get out to large distances. There is really, and the large distances are exactly these lumps. So what we found in the early thing, I can show you the curves, but it's not enough time. We found that we would block down until we got to where these lumps were. And then we couldn't get beyond that. We hit a barrier. So in fact, we didn't completely fail with multigrid. We just couldn't get the whole telescoping down of recursive multigrid. We could go a couple of levels and then bang, we hit a wall, okay? You can think of these things as sort of being like edges, right? Except for they're edges which are dynamically created by the Monte Carlo. So we don't know where they are in advance, okay? And we don't know how they impact the low eigenvalues either. So we have to do it adaptively. So this adaptive method turned out to be just the right thing. Now, this is not a small change in our methodology. Here is an actual lattice, and it's going to get better. And we are running now at the physical quark mass so that this algorithm goes 25 times faster. You get that? 25 times faster. If you optimize a code and you get a factor of 2, you're considered a hero. At 30%, you earn your salary, okay? So my message here is mathematics, mathematics, mathematics. Learn as much as you can. If you don't understand it, talk to people, get the ideas. The mathematicians will never solve your problem for you, but they may tell you how to solve your problem. If you understand the distinction, I mean, they may go off and prove theorems, you may go off and write your code, but when you work together, you will find out things you never thought of before, okay? And 25 times beats a lot of optimizations, okay? That's the good news. The bad news is you got to rewrite your code. So I now will switch to my next application, which is in a sense related to this, and that is hardware-driven. We have now heterogeneous hardware, and we need to program a GPU. So what we did at first, of course, we had the multigrid algorithm, by the way. We didn't program the multigrid algorithm, we programmed the old one, okay? And that wasn't so bad. The GPU in real dollars gives us about a 5 times speed up. That's also nothing to be embarrassed about. And if you can get 5 times as much work done for the same money, you're pretty happy. So now, what do you have to do? We have a whole group that did this, and one of the sort of nice things and sad things at the same time is 2 of our major people, Mike Clark and Ron Babbage, but particularly Mike Clark, who was my postdoc and developed both the multi-grid code and the GPU code with me and this whole group. I can't give full credit to everybody. He could easily be a theoretical physicist, but he's so interested in applied math and computing that he went and got a job at NVIDIA. But they hired him as a QCD physicist. Now, I don't know how long it'll last, but he continues to work with us, probably as strong as he did before, on code and algorithm development, okay? So he is leading a group, which includes now a whole bunch of our application people, to write the best libraries in CUDA, okay? And so, for example, our code, when it runs on the Titan, is using his libraries, plugged into one of the applications codes, okay? So what do we have to do in order to get a good code on the GPU, even the old code? Our problems are completely memory bandwidth bound or network bandwidth bound. So when people tell us we got to worry about location of memory, for our problem, that's not news. We've already been in that problem, okay? It's been the constant problem. So whenever we run on a machine, we basically know we'll get 20% of the flops because that's about the best we can get to pull the data from the memory into the processor and put it back, right? So because people always, even traditionally, over-designed the processor by about a factor of 5 from our point of view. In fact, the GPU is even worse because its device memory is not quite as good relative to its flop rate as a normal CPU. But of course, it's got a heck of a lot of flops. So what we did is we started rethinking about ways we could keep from taking stuff from memory. And we invented a whole group of things. The main thing is, okay, I'll go quickly over this. The main thing is that, first thing we realized, and this has been realized before, I told you we have a lot of these 3x3 complex matrices. Well, if you write a 3x3 complex matrix, you have 9 entries, you have 18 real numbers, you put them in single precision, which is probably okay, and then you have 18 single precision numbers, right? But they're in a group. The manifold of the group has exactly 8 real numbers. But you have to do cosines and sines to get from the manifold of the group back to the element, okay? And nobody in their right mind thought we should do that algebra. It's actually easier to go from, to cut it down by 2/3. You do less arithmetic. It's normal arithmetic. But the GPU has so many flops for sale that are just sitting there hungry and bored. You can do all that arithmetic and you don't even notice it, okay? So we can cut down the data rate from 18 to 8 for every load of the matrix. But now you have to realize another thing. When you invert a matrix, you start off with a very bad approximation. We want it in double precision, but there's no reason to keep it in double precision until you get close, because you're not changing 64 bits of information every time, you're changing a few bits. Now, it turns out because it's a graphic processor, they even have half precision. And half precision is an integer. If you go to look at a unitary matrix, you discover that every entry of a unitary matrix is between 1 and -1. And the architecture exactly interprets every integer, signed integer, as a floating point between 1 and -1 on the fly. Now, you could ask, what about the correlators? The correlator is falling like crazy, huge dynamic range. Certainly we need floating point for that. It keeps going down, 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 right? But no, because we have so much symmetry that every side of my lattice, remember I told there were a lot of variables, okay? Every side of my lattice actually has 24 real numbers attached to it. But they're all rotations of each other, some space rotations and some gauge rotations. And therefore, they all have the same dynamic range. So all you do is save the largest in floating point and the ratios in integers. So that means you get rid of, what was my number? 24. You get rid of 23 out of 24. And you can write those in half precision. So your data rate from the memory just falls like crazy. Now, eventually, after you iterate a while, you have to say, well, I better go to single precision. And then eventually, at the end of a few cycles, you go to double precision. But most of the time, this wins you, a factor of 4. Here's an example. This is the curves when you use less data, and you see how far it goes up from 200 to 500, okay? So this is in a sense lossless data compression. We're getting exactly the same accuracy out the end, okay? So when we read our flops, we do a curious thing. We act as if we were doing this in double precision, because that's the answer. That is cheating in one direction. But we don't cheat in the other direction. All the extra flops that we use on the processor to do compression, we don't count those as flops because we didn't use to count them, okay? So when we say that, right, for example here, when you're saying we're getting these many gigaflops here, we're actually using more because we didn't add all the ones in data compression, right? So remember, you can trade one resource against another, okay? So I think this is a very general lesson, and we could talk about it. There's a lot of ideas along this line. But remember that resources can be traded, and you can even trade floating point against memory, okay? And there's a lot of ways to do this. So anyway, that's a general lesson, I hope. So, the final wrap-up on this is to go one step farther, which I call synthesis. Now we have an embarrassing situation. We can actually run on the CPU the GPU code 25 times faster, or we can write the old code and put it on the GPU and go 5 times faster. Well, that's not very good, is it, right? So now, it's not true for all our code. So some of it we just definitely speed up. But a very important part of it actually is now slower on our beautifully tuned, clever GPU code than our beautiful algorithm on our CPU. So it's just a lesson. You must put the best algorithm on the best architecture. But of course, the architecture has to be friendly to that. Now, it turns out, amazingly enough, it looks like this is still work in progress. I'll show you the curve here. This is the flop count. I'm sorry, the clock count between the GPU multigrid and the old multigrid. So you see the thing is converging. I'm sorry, it's convergence rate. It's converging like a bomb when we use multigrid. Now, it turns out that actually multigrid is pretty friendly for a GPU, because we do actually the opposite of what I thought we'd do at first. We put the big problem on the GPU, okay? And when the thing telescopes down and gets small, we go back to the CPU and use it, right? It's the weak processor, right? It's the co-processor, of course, right? You have to think differently. The GPU is the processor, right? The CPU is for doing little bookkeeping and running the network, okay? It's the only way. I mean, this is the way it should be thought of in the future. I'm totally clear. Okay, so anyway, this is the kind of thing. The other thing we have to do is when we spread it across many GPUs or many CPUs for that matter, we hit the communication bottleneck of the network. So now we're doing block decomposition, so-called Jacobi, simple by the block Jacobi, the simplest thing. We're doing this to get a slightly worse algorithm, but with fewer communication steps. Okay, so we're doing block Jacobi to cut down the network traffic. These together make a huge difference. I mean, these are not minor things, and they're not all, by the way, in our codes, because we have to do a lot of recoding to do that, okay? Maybe we don't have a good enough factorized code the way we were told to do it. Trying our best. Okay, now, one thing I'll end with. Everything we're doing in terms of concept is going to go over to the PHY. We'll have to reprogram, of course. It's not, although I'd love to see a standard evolve. But the lessons are general. You know, it's just a question of the heterogeneity and how we break things up. The other thing I would like to point out, and I don't know as much about Intel, so this is not to say that I'm not, but we go for anybody. We have no loyalty except for, I have a friend in NVIDIA, so I suppose I should somewhat. But, you know, NVIDIA, and I'm sure the PHY roadmap is very similar. They decided not to go beyond the Maxwell to sort of they were going to have another one. I can't remember what they're going to call it there. But they junked it and decided to take a big jump to Pascal, which is somewhere in, I think they were saying more like the end of 2.15, but maybe 2.16 is more realistic. Two very important changes are taking place, which is exactly what everyone wants, but we are really eager to get. They have a fast link, which they call NVLink, which they're co-developing with IBM. They also have a collaboration with IBM. And so this link will directly go to the power system in IBM. And it is a much faster link than the PCI Express, which is the way you got out of it. They also have stacked memory, which is also coming generally in, which has more power efficient and also much faster. So now, with the Pascal, Even if they didn't have more cores, I'm sure that we will get a full teraflop sustained on our entire code on a single chip. Now, I'm old enough to realize when we wrote this $200 million thing to have a teraflop machine, which was going to solve all our problems, okay? Now they're on a chip, okay? So I'm not sure where the programming models are going, and I'm not sure where architectures are going, but I'm sure that this next step is going to be terrific, and we will program it however we can. I am concerned that it is taking more and more effort, okay? And we've got to get smarter. I mean, I don't want to be any dumber than I have to be, okay? I'm also concerned, and I'll say this one last thing. Oh, yeah, I should say, we are building frameworks to try to control the complexity. This is an interesting thing. We are now running, since we have all of these disparate kernels, if you like, or libraries, one of the approaches to running this thing is actually to use a scripting language. A runtime, it's not a compiled, it's an interpreted language. It's called Lua. Does anybody know what Lua is? Okay. And for our C colleagues, we can make Lua look as pretty as a C++ interface because it's just text, right? Make it nice. And this is allowing us, so for example, the CUDA library has got all kinds of modules, a little hard to use. It can be input into a full application code, but we're going to drive it actually by script language. And the scripting language has the advantage that we're getting more and more tunable parameters. And the parameters have the same name even when we change from one theory to another. You know, maybe a different gauge group. Gauge theories are actually useful for condensed matter. They're useful for beyond the standard model, beyond QCD. We hope there's new stuff. So in Fuel, we don't say what kind of field theory we're running, just that it has certain attributes. And so when we have a force, it's a force, even have to be computed differently below. And this means we can expose all of the parameters, which are getting to be extremely numerous. I haven't described the whole evolution, but we have a Hamiltonian evolution to go through the Markov process. And it has now dozens of control parameters to make it efficient. Now, multigrid is going to have another dozen parameters. So first of all, it's much nicer to expose those parameters so you can play with them and try to optimize, and even better to auto-tune them. In fact, we're already auto-tuning our CUDA. Each module in CUDA is split up in the symmetric processes and warps in a different way, specifically for that one. There's no uniform split up of our code. Each call, function call, is automatically auto-tuned to the sweet spot, okay? And I think this is also something we're going to have to do. So I think that we'd like to have better methods, and I'll end with one more plea, and that is we badly need a formula translation language. Does anybody know what it should be called? It's a joke. I don't want to program in Fortran. But there was an attempt way back when to make a formula translation language. And the other thing I might say is that the connection machine was a one-off special machine, but it had wonderful applied mathematicians and computer scientists. And Leonard Johnson was one, and he wrote a fantastic scientific library which had primitives. It had ways to do gathers, scatters, blocking, translations, and so on. It also had a lot of higher-level linear algebra, but it was really a whole language of parallel primitives. So when I programmed the connection machine and I wanted to invent a new algorithm, I didn't have to do any explicit parallel programming. I could write directly new algorithms in parallel. And that's because they didn't just deliver a naked machine like these rich companies. Since it was a research company, they delivered what we all ought to demand the machine be delivered with, and that is very good toolbox of parallel operations. Anyway, so thank you very much.